Settled in the picturesque city of Geneva, Switzerland, the European Organization for Nuclear Research, commonly known as CERN, stands as a beacon of scientific discovery and innovation. At the heart of CERN's mission is the quest to uncover the fundamental building blocks of matter, exploring everything from the tiniest subatomic particles to the vast expanse of the cosmos. Among the groundbreaking research conducted at CERN lies the intriguing story of antimatter, a cornerstone in the puzzle of why the universe exists at all. The enigma of antimatter. Antimatter, often depicted as a concept from science fiction, is a fascinating mirror image of regular matter. With properties nearly identical to matter but opposite in charge, even a minute interaction between antimatter and matter would unleash energy comparable to a nuclear explosion. This paradoxical substance has captivated physicists for decades as they attempt to unravel its mysteries. The importance of studying antimatter lies in its potential to answer one of the universe's greatest questions. Why is there more matter than antimatter? Scientists believe that during the universe's infancy, following the Big Bang nearly 14 billion years ago, matter and antimatter should have existed in equal amounts. However, today, antimatter is conspicuously scarce, leaving researchers pondering where it all went. Did it vanish due to an unknown quirk in the laws of physics, or does it still exist in isolated pockets, far from our observable universe? The discovery of antimatter. The first theoretical hints of antimatter emerged in 1928 when English physicist Paul Dirac formulated a groundbreaking equation that unified quantum mechanics, electromagnetism, and Einstein's theory of special relativity. Dirac's equation suggested the existence of a particle with the same mass as the electron but with a positive charge, a particle he called the positron. Although the idea was met with skepticism, Dirac's faith in his equation proved justified. In 1932, Carl Anderson at the California Institute of Technology detected a positron while studying cosmic rays using a newly designed particle detector. This discovery confirmed Dirac's prediction, marking a significant milestone in physics. Yet, the revelation of the positron only deepened the mystery surrounding antimatter. While electrons are abundant, positrons are exceedingly rare, raising questions about why antimatter appears to be nearly absent from the universe. The cosmic puzzle of antimatter's absence. One early hypothesis posited that antimatter might exist in distinct regions of the cosmos, perhaps forming entire stars or galaxies. However, this idea was soon debunked. When matter and antimatter come into contact, they annihilate each other in a powerful burst of gamma radiation. If antimatter stars or galaxies existed, their interactions with matter would produce detectable gamma rays. Yet, decades of observations using sophisticated detectors have revealed no evidence of such radiation, suggesting that antimatter objects are extraordinarily rare or non-existent in our universe. The role of CP violation. In the 1960s, a crucial clue emerged. American physicists studying kaons, subatomic particles, discovered a phenomenon known as charge parity, CP violation. This effect demonstrated that antimatter does not perfectly mirror the behavior of matter. Although the observed CP violation was minor, Soviet physicist Andrei Sakharov proposed in 1967 that such asymmetry might explain why matter outlasted antimatter after the Big Bang. However, for this theory to fully account for the matter-antimatter imbalance, CP violation would need to be both widespread and significantly stronger than observed. Modern investigations at CERN. To explore these questions, researchers at CERN and other facilities have built massive particle colliders that recreate the high-energy conditions of the early universe. By smashing particles together at near-light speeds, these experiments produce exotic particles, including antimatter counterparts, allowing scientists to study their properties and behaviors. In 2001, experiments at CERN's Large Electron-Positron Collider and similar facilities in Japan provided new evidence of CP violation in particles beyond kaons. Although these findings validated theoretical predictions, the degree of CP violation observed was insufficient to explain the vast dominance of matter in the universe. This suggests that the standard model of particle physics, while highly effective, may be incomplete, pointing to the existence of new, undiscovered phenomena. The broader implications. While the study of antimatter may seem removed from everyday life, it holds profound implications for our understanding of existence itself. By uncovering the mechanisms that favored matter over antimatter in the universe's earliest moments, scientists are delving into the fundamental nature of reality. This research not only addresses a cosmic mystery but also deepens our knowledge of the universe's origins and our place within it. As CERN continues its groundbreaking investigations, the enigmatic story of antimatter remains a testament to humanity's relentless curiosity and ingenuity, pushing the boundaries of science to uncover the secrets of the cosmos. Antimatter has long intrigued scientists, especially its interaction with gravity. While theoretical predictions suggest that matter and antimatter respond similarly to gravitational forces, the challenge of studying antimatter directly has made it difficult to confirm. This difficulty arises because antimatter annihilates upon contact with matter, requiring extreme precision and innovative methods to handle and study it. Antimatter in the lab. The Alpha experiment. For the past 2 decades, researchers from the Alpha collaboration at CERN have been pioneering the study of antimatter. They have developed techniques to produce and trap antimatter, starting with high-energy antiprotons created in the CERN proton synchrotron. These antiprotons are slowed down to manageable speeds, equivalent to a few hundred feet per second, and cooled to temperatures just 15 degrees above absolute zero. The antiprotons are then combined with positrons, anti-electrons, which are derived from the decay of radioactive sodium, to form antihydrogen atoms. Antihydrogen, the simplest form of antimatter, mirrors hydrogen in structure. A negatively charged antiproton serves as the nucleus, orbited by a positively charged positron. Previous experiments confirmed that antihydrogen atoms emit and absorb light at the same frequencies as regular hydrogen, consistent with Einstein's predictions. Testing gravity's effect on antimatter. Directly observing how antimatter interacts with gravity has been a monumental challenge. Gravity is far weaker than the electromagnetic forces used to manipulate antimatter in experiments, making precise measurements difficult. In a recent breakthrough, the Alpha team confined antihydrogen atoms in a magnetic trap inside a 10-inch metal chamber. The trap relied on the slight magnetic properties of antihydrogen to prevent the atoms from touching the chamber walls, where they would annihilate. By gradually reducing the magnetic field, researchers observed how the antihydrogen atoms behaved. Approximately 80% of the annihilation events occurred at the bottom of the chamber, indicating that gravity pulls antimatter downward just as it does with ordinary matter. This marked the first direct measurement of gravity's effect on neutral antimatter. The matter-antimatter imbalance. The experiment confirmed that antimatter behaves as expected under gravity, but it leaves a deeper mystery unresolved. Why does the universe predominantly consist of matter rather than a mix of matter and antimatter? According to the Big Bang theory, equal amounts of matter and antimatter should have been created, leading to mutual annihilation and leaving nothing but radiation. Yet, the observable universe is overwhelmingly composed of matter. This imbalance might stem from a phenomenon known as CP, charge parity violation, which causes subtle differences in the behavior of matter and antimatter. Experiments, including those at the Large Hadron Collider's LHCb detector, aim to uncover whether CP violation is sufficient to explain this asymmetry. However, results from the Alpha experiment offer no new clues on this front. Antimatter in the universe. Antimatter remains elusive outside of particle collider experiments and cosmic ray showers. If antimatter existed in large quantities, its interaction with matter would produce high-energy gamma rays, which we do not observe. This absence suggests that stars, galaxies, and the universe as a whole are predominantly made of matter. If the universe were composed entirely of antimatter, it would appear identical to our current universe. Antimatter particles, like their matter counterparts, combine to form atoms, molecules, and larger structures. However, the annihilation of matter and antimatter at their boundaries would leave a detectable signature of gamma rays, which is not observed. Antimatter black holes. A thought experiment. Even black holes, which are defined by their mass and not their composition, would behave identically whether made of matter or antimatter. According to Einstein's general relativity, The properties of a black hole depend solely on its mass, electric charge, angular momentum, and potentially magnetic charge. These attributes, often called the hair of a black hole, do not distinguish between matter and antimatter origins. Conclusion: the study of antimatter continues to deepen our understanding of the universe's fundamental nature. While recent experiments have confirmed that antimatter responds to gravity in the same way as matter, the mystery of the matter-antimatter imbalance persists. Future research, particularly on CP violation and the behavior of neutrinos, may one day illuminate why the universe exists as it does. Until then, antimatter remains both a scientific challenge and a profound cosmic enigma.